Section 14.5, Directional Derivatives and Gradient Vectors. So here's a list of some learning goals that you should be able to have accomplished by the end of this section. You should be able to compute the gradient, know its properties. You should be able to apply the chain rule for paths, be able to find directional derivatives, and know how to find tangent planes to 3D surfaces. Okay, so what is the gradient? The gradient's going to be the most important thing going on here. And so the guiding principle is this thought. Rates of change of a function of several variables, 2 or 3 variables, depends on the direction. Now, this is the whole idea behind partial derivatives. The rate of change you move in the x direction of your function is probably going to be different than the rate of change you move in the y direction. And so our question here is how to summarize. Is there a way to just kind of take all of the information that we might have about all the different possible rates of change and summarize it into one single expression? And so to kind of do this, let's actually do an example here. So here's a function of 3 variables. F of x, y, z is equal to xy squared plus e to the z. And so it's not too hard to compute that the x derivative is equal to y squared. The y partial derivative is equal to 2xy, and the z partial derivative is equal to e to the z. So these 3 partial derivatives, we're going to take them all together, and we're going to smush them together into a single vector. And so this is going to be what we call the gradient of f. So the gradient of f is going to be what you do here. Gradient f is equal to the partial derivative with respect to x, the partial derivative with respect to y, partial derivative with respect to z, written as a vector. So this is what the definition of the gradient is, and the nice thing here is it's a single quantity, it's a single vector, but it summarizes all 3 of these partial derivatives. It gives us information about the rate of change in the x direction, the rate of change in the y direction, and the rate of change in the z direction. Before we go on, let me just point out a little bit of terminology and I guess more notation here. So I want to draw your attention to this symbol right here. So first off, because the gradient f produces a vector here, I put a little vector sign over it to remind us that the answer needs to be a vector. The textbook just boldfaces everything, but I put that little vector sign here. This little symbol right here, I think the more modern name for this is the del symbol, the del operator, del f. You'll also occasionally see an older term sometimes gets used sometimes this is called nabla, and so my source right here tells me that it resembles an ancient Assyrian harp called a nabla. This looks like a harp to some people, so that is why some people call it nabla. Del is what I'll usually say del f for the gradient of f. Okay, so this is the definition right here of the gradient of f. I've written out the gradient of f here for this is a function of 3 variables. If your function is just a function of 2 variables, guess what? Your gradient will just be a 2-entry vector here. And so, in fact, let's just do that right here. So suppose that your function f of xy is x squared plus y, the gradient, so f sub x is going to be 2x, and f sub y is going to be 1. And so I think I want to do with this is just to kind of observe here the importance of making sure you understand what the gradient actually is. So let's just calculate the gradient at a couple different points. At the point, let's say 0, 0, this is the vector when you plug in x is equal to 0, 0, comma 1. At the point 1, comma 1, this is the vector 2, comma 1. So what the gradient operator does is that for each point in the plane, let me write this out here. For each point in R2 or R3, depending on whether you're working with a function of 2 variables or a function of 3 variables, the del f, the gradient f, associates a vector to that point. So at the point 0, 0, the origin, we have a vector, the x component is 0, the y component is 1. Okay, just like that. At the point 1, comma 1, so right here, the x component is 2, and the y component is 1. At the point 1, comma negative 1, you also get 2, 1. So let me just point out here. So there's the gradient vector drawn. There's the gradient vector drawn at three of these points here. So the gradient vector, it inputs a function of 2 and 3 variables. It outputs a vector in with 2 or 3 entries, 2 or 3 components to it. And really, but these vectors are a function of x and y, or x, y, and z. And so really it's associating a vector with each point in the plane or each point in 3-dimensional space. So that is what is going on here with the gradient. And let's see here. Yeah, this will be a good time for our first pre-class problem. So if f of x, y, z, so function of 3 variables, z e to the 2x plus 3y. So compute the gradient of f. So this symbol, this terminology means compute the gradient f and evaluate it at the point x is 3, y is negative 2, and z is 4.